A new paper has argued that some of the levels of organic materials in mudstones on Mars are unexpectedly high for a non-biological world. Let's take a close look at this and see what it's really telling us, because potentially this is quite exciting. Hello again. As many of you know, I'm a purely earthbound paleontologist, but that doesn't mean I don't have an interest in life out there. Because I'm one of the people that's pretty convinced that life is going to become quite common once we know how to look for it and once we start finding the evidence. So, astrobiology is this weird subject where we're trying to establish the ground rules for extraterrestrial life, for life elsewhere in the universe, and trying to find evidence for whether it exists or not. And so I have a very strong interest in this. And every now and then, when there's an interesting new bit of development coming up, I will dive into it and explore from a sort of geologist perspective, really, what it's actually telling us, whether there really are alternative explanations, whether they're getting really contrived, or whether we should start thinking that maybe, just maybe, this is the evidence we're looking for. So, this new paper goes back to a previous paper from last summer where the discovery was announced of alkanes, so long-chain carbon molecules from it was 10 to 12 carbons in a chain from a mudstone in Gale Crater. This is the paper by Freycinet et al. Using the Curiosity rover's sample analysis module. Sample analysis at Mars, SAM, okay, which is basically a pyrolysis device. It heats a sample and then analyzes the material given off by the breakdown of that sample. And what they found was chains of carbon 10, 11, and 12 carbon atoms long, alkanes, which is significantly long. It's longer than the similar chains that we get on asteroids like Bennu and Ryugu, for example, where we've actually had sample return missions and can analyze them in Earth-based labs. So these are quite large structures, and they believe that they were the breakdown products of fatty acids. So these are lipids. They're quite complex organic molecules. They are not definitive biomarkers in any way. We don't know we know that they don't form exclusively by life, but they are very characteristic of living things. And unfortunately, you do get fatty acids in interstellar dust particles, for example, and meteorites. So it's not in itself a biosignature. But it's interesting, and especially to see it in a mudstone. It means that within this sort of circulating biosphere, hydrosphere system, where sediment was being washed downstream by rainwater and so on, you have long-chain alkanes being incorporated into that sediment. It was part of this circulating system of organics and non-biological materials. So that was interesting in itself, but it wasn't enough to say anything particularly about the history of life on Mars, potentially. It does make Mars more habitable, that there were large amounts of organic material, or at least significant amounts, but it doesn't tell you anything about whether life was actually there, despite the fact that it is things like fatty acids. One thing that's quite important to realize is that the amounts that they were detecting are very low. We're talking about 30 parts per billion, which is small. That sort of trace amounts, effectively. Significant, but still very low quantities. That was the previous paper. The new paper has taken this and extrapolated a little, because they realized, quite critically, that this sample has been exposed on the surface of Mars for a long time. The sample was taken from just below the surface, where the Curiosity can drill into the rock a little way, take out that sample and analyze it. So it's not actually on the surface, but it's been exposed for a long time. And we know that this part of Gale crater, well, the Gale crater itself, was formed something like 3.5 billion years ago. So in the early days of Mars, when there were still oceans and flowing water everywhere. But for most of that time, we also know that the surface rocks have been covered over by sediment or by drifting sand or something. Because when you have cosmic rays striking the surface and Mars having a very thin atmosphere, that happens a lot. It has effects on the chemistry and creates isotopes of things which you can not expect to find there through any other source. And so we can actually analyze this, and this has been done in a series of previous papers, to look at the range of different isotopes that are present in the surface rocks in that part of Gale crater, and have found that there was something like 80 million years of exposure to cosmic rays in these surface rocks. So this is a direct measurement of the rocks in the vicinity. Not exactly the same ones, but the same region, the same part of the crater floor, and probably this is pretty reliable. I mean, there are significant error bars of 10, 20, 30 million years, but around 80 million years for 3 different isotopes, they came to the same conclusion. So 80 million years of exposure to cosmic rays will do a lot of damage to long organic molecules. It will break them down into smaller pieces, and you will eventually lose most of your organic material. And this is a well-studied process. We actually have equations to let you calculate what was going on here, and let you calculate backwards to, if you have a certain concentration today, what that concentration must have been like in the past. So, Pavlov et al., 2026, have rewound that clock. And what they've come up with huge error bars for various reasons, there's a lot of unknowns here, is based on 80 million years of exposure to cosmic rays on the surface of Mars, a range between 120 and 7,700 ppm of these organic molecules. This is the C10 to C12 alkanes. That's quite a bit. 120 is not very much. 7,700 is actually a lot. That's 0.7% organic material. Okay, let's take this a little bit further though, because this is very much a conservative estimate. So there's reasons why it is expected to be actually originally even higher than that. So if we take something like a mid-range of, say, 3,000 ppm, it's still 0.3%, but there are several reasons why it should probably be higher. Firstly, this only reflects the breakdown of the organic material by cosmic rays. On the surface of Mars, there are also perchlorates, which will oxidize, break down organic material relatively quickly as well, and these are a major factor in what happens to things on the Martian surface. So we can probably assume that there's an extra multiplier for having perchlorates involved as well. But that's not the worst one. The original measurement was for a narrow range of alkane lengths, the C10 to C12 lengths, 10 to 12 carbon atoms, which are breakdown products of probably larger molecules as well. But that was what was being detected. It's not just that there weren't any smaller and larger than that, it's that they weren't detectable by that particular technique. It was focused on this range. So on that basis, assuming that there are lots of smaller organic molecules there which have already been partly broken down, and larger ones which have been broken down less, that could multiply the values that you're getting significantly. I mean, potentially an order of magnitude. We don't know. It's a large amount of increase that you would expect to see if you take that into account, because it's only a small range of the possible organic molecules that were likely in that sample that were detected, which are being quantified here. So that's actually a really interesting point. That starts to bring it up to quite high levels potentially. There are other aspects as well, like the surrounding rock appears to contain sulfates, and there's some evidence that where you have sulfates rather than silicates, that tends to encourage the breakdown of organic material just because of the behavior of cosmic rays going through it, and so on. So everything that we have here seems to be pointing towards these samples actually being an underestimate of the amount of organic material. And the authors suggest potentially even orders of magnitude higher. 1 to 2 orders of magnitude would put that 0.3% up to, well, 3%? 30%? That's way too high. We're talking, that's a lot of organic material. So how much are we talking about here? I mean, I know these percentages won't mean much to most of you, so we need to actually bring this down to Earth, as it were. On Earth, we have a lot of information about the total organic carbon content of mudstones because it is intensively studied for things like source rocks for oil and gas. And an organic poor mudstone is considered to be less than 1%. So that 0.7% that we get on Mars as the maximum of their estimated range, which is also a minimum, if you see what I mean. But that sort of range, less than 1%, would make it organic poor on Earth. But this is a world that is steeped in biomass. The really high levels that you get are around sort of source rocks and so on, and there you're looking at 2 to 4% organic carbon plus. Now, I've worked in some rocks in China from the early Cambrian, which are known as the stone coal, because there's so much carbon in these things, you can burn the rock. And those are getting on for about 10% organic material, but that's extreme. I mean, you hold the rock and it smells like oil. So that's unusual. The range 1 to 10% covers mudstones that are not organic poor on Earth, with a thriving biomass which has been going for a long, long time and has learned to recycle effectively. So on Mars, if we're talking about an original total organic carbon, TOC, of something in the similar sort of range, maybe 0.5 up to 3 or 5%, that is remarkable. That is not what you would expect at all. Now, their estimates, remember, the official estimates are 0.01 up to 0.7%, so it is less than that, but there are reasons for thinking this is probably a gross underestimate. Okay, that's a comparison with Earth-based mudstones. We can also look at the composition of asteroids like Bennu and Ryugu, where we've actually had sample return missions and are able to look at the content of them directly. And there it seems that they are around 3 to 4 weight percent organic compounds, which is impressive. And it's a wide range of compounds as well, things like amino acids and sugars and alkanes, indeed. But those alkanes are much shorter, or significantly shorter at least. So they're less than 12 carbon atoms long in meteorites, and in Bennu and Ryugu it was less than 7 carbon atoms long. So that, of course, could be due to even longer exposure to cosmic rays as these things are flying around in space. Although the samples were taken by basically impacting the surface and then picking up the bits that were flying off. So it's not totally clear how much that would have been protected by the surface layers, but basically they have been affected by cosmic rays, and maybe there were naturally, originally, larger organic molecules that were broken down while on the surface. That said, of course, if they're in the interstellar or interplanetary medium, they're always being bombarded by cosmic rays, so how do you get much bigger molecules forming in the first place? So there's a bit of an unknown there as to how big these molecules can get in asteroids like Bennu. If we were to drill down into the core of it and pull something out from the middle, what would we find there? We're not sure. But again, 3 or 4% is an interestingly high proportion of organic material in total. But that is not normal for the rocks that you get on planets. These carbonaceous chondrites are part of a sort of primordial, a very primitive compositional pattern of the early solar system material. And when things are turned into planets, which then have potentially tectonics and outgassing and all sorts of things going on, internal heating, a lot of that ends up being broken down. You end up with carbon dioxide, methane, and so on. And so you have a different sort of range of carbon bearing compounds than you do in these pristine bits of material. But it's interesting seeing this direct comparison. And critically, of course, we just don't see this level of organic material in samples from other planets as a matter of course. It is not normal. So something has been going on here to concentrate not just organic material, but long chain organic material, and potentially originally much longer than the 10 or 12 carbons that we're seeing here. So, how do we go about explaining this? Pavlov et al. Actually do a really good job at going into these possible explanations, assessing them, seeing whether they work, and where the uncertainties still lie. They are not coming down on this being definitely life or anything of that sort. They're being very careful in how they phrase things, which is exactly what you want to see. So, first of all, you have to look at the possibility of simple deposition of interplanetary dust particles and meteorites, which would build up on the surface and give you a significant significant organic component. And there have been prior estimates of how much material could build up from that sort of mechanism. And those estimates suggest something like 500 parts per million if it's exposed for about 3 billion years. So that requires a lot of material exposed for a long time to gradually fall through the atmosphere or pierce through the atmosphere in the case of meteorites, but dust settling quite slowly after each terminal velocity. And these things will gradually accumulate and potentially give you a large amount of material in the long term. However, this is a calculation that affects the regolith, the soil on the surface. What we're talking about here is a layer of mudstone. Now, of course, you can get sort of meteoritic material getting incorporated into mudstones, but normally you have to have an impact which breaks up the rock and introduces that material directly into it. And this has not happened here. We're talking about a nice intact layer of mudstone that shows no evidence of being hydrothermally altered or broken up or damaged in any way. So that sort of mechanism, even if it could somehow be multiplied to get to the sort of levels that we're talking about in 80 million years, couldn't get them into the mudstone. Not in any quantity. So we can probably rule that one out entirely. It's not just simple accumulation on the surface. How about a methane-based organic haze during the early atmosphere? Because, of course, we're going back originally to the formation of the crater being something like 3.5 billion years ago, and we don't know at what time or times since then the crater floor has been exposed. Now, the mudstone is likely to have formed during this early phase, immediately after the creation of the impact basin, which led to the runoff creating rivers which pooled into this basin as basically a sea. So at that point, we are looking at probably 3 to 3.5 billion years ago, and there may well have been a very different atmosphere then. Now, that may have included a lot of methane, which can react in complex ways to give you alkanes, which potentially can give you a buildup of organic material of various types. Now, this has been modelled. I believe it's quite a complicated process. I don't understand all the details, is what I'm saying there. But modelling of this atmosphere doesn't give you anything like enough volume, even of methane, let alone of the long chain alkanes, to give you the results that we're seeing in this mudstone. So based on that, it looks like we can rule that out as well. I can't comment on whether that is valid or not, but it sounds pretty convincing the way they write it. Then you have the third option, which is the one that they can't rule out. And this is hydrothermal alteration. So igneous rocks do include organic compounds. I mean, this is quite well known. We see it on Earth, and it is incorporated into the mantles of planets. And those compounds can be affected by hot water percolating through cooled igneous rocks. So things like basalts and so on can have cracks in, water percolates through, and you get reactions going on in this sort of interval. And one of the main reactions that happens is the serpentinization of mantle material. And this is where you go from things like olivine to minerals like serpentine. It's a complex suite of inorganic chemistry, but one of the byproducts of it is the release of methane. And this is something which I'm sure we'll come back to when we talk about the methane spikes on Mars, which is another really interesting story. But production of methane in these situations with hot water means that you can get reactions happening, often catalyzed by other minerals in the area, potentially giving you long chains of organic material. So that is a potential source of producing large organic molecules. Now, the amount of organic material within these igneous rocks originally should be quite low. I think from Martian meteorites, which are from the sort of mantle materials, it's something like 12 ppm, parts per million. So it's very small quantities. But you can get those focused into small areas potentially through hydrothermal activity. Okay, now the hydrothermal activity that we need here did not happen in this mudstone. There is no evidence for it. It is not altered in that way. There's no fracturing through it that could explain it. So we are not talking about the rock itself having been the host to hydrothermal activity or having been a direct outflow from this activity. So you could have serpentinization at depth, which could sort of run up through the crust and deposit organic molecules within the mudstone. That is not what could have happened. We still need the release of that organic material and then the concentration of it into sediments, which were eventually laid down and deposited as these mudstones. That's where it gets more complicated. We know that those long chain carbons can get up to about carbon 18 in experimental settings, so that fits perfectly, but we still need to get it from there into a mudstone in high levels. So what we'll be looking at is something like hot spring deposits where you have upwelling of hydrothermal fluids, which releases a relatively high concentration of long organic molecules, and then somehow you have to get those in high concentration into a mudstone. How viable is this? The authors say they cannot rule out the situation where it was a hydrothermal source due to serpentinization going on somewhere else, and you have a redeposition of those organic materials in these beds. They couldn't rule it out. They don't have enough information to say whether it's viable or whether it's not. And at this stage, it's on the table. So we can look at how viable this is. So if we assume hydrothermal fluids upwelling from a serpentinization zone deep underground, we can assume that that made it to the surface somewhere through something like a hot spring. And there probably were quite a lot of hot spring deposits in the early Mars. There was a relatively thin crust at that point. You'd imagine a high heat flow, lots of outgassing. There would have been fractures. Lots of asteroid impacts would have given all this cratering. So yes, I can certainly imagine hot spring deposits being a thing. But can you concentrate them then? Well, the problem is possibly. There are so many unknowns that it is very hard to rule it out. But I can put together a scenario where it might just about work. So imagine a drainage system. This is in an upland area with hot springs bubbling away. That is part of a catchment area, probably quite a small area so that it isn't diluted too much, where the springs coming out into streams, which then flow down, eroding the surrounding rocks on their way, until they hit a lake. Now, this lake might be, for example, wide and shallow and quite sort of still. It might be, for example, Gale Crater. And you could have an outflow from that lake, which would probably have to be underwater. So this area of Gale Crater, it might not have been an entire ocean basin. It might have been sort of isolated into pockets at various points. So there may have been localized lakes where there was an outflow below the level of the surface of the lake, like a little underground conduit, going down a lava tube or cave system or something like that. The reason that that is important is that that gives you a way to concentrate the fatty acids because they are lighter than water, less dense. So they would then potentially build up on the surface of this lake deposit while the water drains away them underneath that layer and is constantly replenished with more organics coming in. It basically forms an organic trap. And at that point, you can have a situation where you do get high levels of organic material, potentially forming a sort of a surface layer on the water. Now allow that to become a seasonal lake, and the water evaporates, drains away. You get a mass of organic material deposited on the lake floor. Rinse and repeat. Eventually, you end up with a reworking of these concentrated organic layers with the muddy sediment, and you can end up theoretically with an organic rich sediment. Probably on the sort of level that we're talking about. I am plucking this idea completely out of the air. There's no reason to think that that actually happened. We don't know if that scenario was in existence in that area at all. What I'm trying to do here is not to show you what happened, but to find a way in which it could have happened. Because that's what we're having to do when we're trying to rule out alternatives to a biosphere. Obviously, if there was an entire biosphere of microbial or even multicellular, who knows if they use cells, life living around these watercourses, then that gives you a perfect sort of way of getting lots of organic material. No problem there. The question is, does it have to be that? And we're trying to look at ways in which you could get around it. And a situation like this might be a way of, in a localized area, getting a high concentration of long-chain organics, including fatty acids, being deposited in a layer of mudstone. Do I believe it? Probably not, but on the other hand, it is a geologically plausible scenario. Areologically. Martian. We could refute this idea, potentially, by finding the same pattern across wide areas. The more you have to multiply this high concentration by a large volume, the more it becomes implausible. If you find it in different regions of Mars, if you find the same sort of high density of long-chain alkanes turning up all over the place, then again, it really becomes much less plausible. And at that point, you're looking at pretty much a direct comparison with mudstones on Earth. So we're not talking about a situation like that. We're talking about a relatively localized source of serpentinization underground, which is leading to a localized concentration that can generate what we see in this one sample. Of course, if we had a geologist on hand with a hammer, then they'd probably be able to sort this out in a matter of hours, just by going and looking at the rocks, looking at the textures. there should be, if this was laid down by life, some trace of microbial textures, fabrics, sort of algal mat type structures over the surfaces. There should be something there which would be visible to a geologist that wasn't tied to commands from NASA to go and look at X bit of rock and drill into it and so on. Just give me a good hammer any day. But I mean, it's incredible what we can do with these rovers, but we have to understand how limited it is as well. And it is pretty limited. So I would absolutely love this to be evidence of life. Evidence of not just life, but a thriving biosphere on the scale of what we see on Earth in the early days, at least. But we can't claim that from this. The authors aren't claiming that from this. They're being very careful and very balanced. What we're doing, though, is narrowing down the ranges of possible explanations, and this is a really vital step in the process. So if you look at the video that I did on these leopard spots, this supposed geochemical evidence that seems to be pointing towards life as well from last year, then you have a really interesting pattern there as well. And my only way of explaining it inorganically was again through local hydrothermal activity and combined with low pH acidity as well. And this looks like it might be a recurring theme. We've got now two bits of evidence that might point to life. The only other explanation involves hydrothermal activity and serpentinization especially. We've also got these methane spikes where the only non-biological interpretation seems to be a combination of seasonal sealing of the surface of the planet by ice and serpentinization still going on at depth under the surface. So we are now fitting into really two schools of thought. We have a biological explanation on the one hand and a serpentinization and hydrothermal activity explanation on the other. And this is important because it allows us to then target what we're testing. There could be studies done looking specifically for evidence of ongoing serpentinization. I'm not sure what lines of evidence those would be, but I suspect there would be some chemical analyses that could be done, maybe atmospheric, which would be looking for exactly that signal, which would be a slightly different signal to what we're seeing in these potential biosignatures. And it's really fascinating. I mean, when you're trying to look for life on another planet, it's not just as simple as finding lots of organic material and saying, aha, obviously. But you have to consider the planetary system, the geochemical system. Life, in a sense, is a subset of the geochemical system. It is a bit of organic chemistry, but there's lots of organic chemistry that goes on without life. So it's a more complex bit of it. And even defining the boundary between life and non-life is, of course, a fool's errand in some ways. We still haven't got a clear definition. But the point is that it is a gradation between inorganic, i.e. non-living, and organic living chemistry. So it's a really fascinating area, and you can see why people get tied up in knots and why it's so hard to actually give a definitive answer. But is it aliens? I don't know. Is it? You tell me. I'm waiting for the next story personally. But I'm looking forward to it because there is a long way to go in this, and one day, surely, it has to be life. Maybe. So thank you for listening. This is, I know, a slight deviation from my normal sort of pattern, but I like astrobiology, so you're getting some too. And it actually all fits in really neatly. This is part of what we're doing here. It's not just looking at one particular thing. It's seeing life as a process and a phenomenon and trying to understand how it all fits together, and particularly how we fit evidence together. Because that usually isn't as simple as it might appear at first glance. All right then, see you again. Bye for now.